Okay, so our next speaker is Georgina Falster, who's going to talk us about, from the University of Adelaide, talking about the role of Indo-Pacific SST variability in global drought occurrence. So you have 12 minutes, and I'll give you a 2-minute one. Oh, yeah.
All right, so this morning I'll be sharing work that Nerali, Spencer, Zoe and I have done using the ACCESS-ESM to test a hypothesis derived from the paleoclimate literature that there is a link between the magnitude of variability in tropical Indo-Pacific sea surface temperatures and droughts across the mid-latitudes. Now, I know this is maybe a bit outside the wheelhouse for a lot of you, but it's also outside my wheelhouse, so that's fine. We'll all muddle along together, hopefully. All right, so this talk deals with droughts, specifically multi-year droughts, and how they're affected by Indo-Pacific sea surface temperatures. So to set the scene, I'm showing this graphic that shows the percentage of times a particular phase of ENSO, or the Indian Ocean Dipole, is associated with drought onset across Australia. And so in the top row, we can see that El Nino events are associated with drought onset a lot of the times. This is from the historical record, but not La Nina events. In the bottom row, we can see that positive IOD events tend to be associated with drought onset more than negative IOD events. So it's pretty clear that what's happening in the tropical Indo-Pacific is important for understanding drought occurrence across Australia. And it's not just Australia, but across the mid-latitudes. So for example, in the Horn of Africa and the southwestern US, where opposite to Australia, La Nina events are associated with droughts, or Southern Africa, where ENSO and the IOD combine in quite a complicated way also to affect drought occurrence. And so there's also evidence from the paleoclimate record to suggest that there's even more to the story than just ENSO and IOD phase. So here I am showing a graphic from Nerali Abrams' 2020 review paper summarizing climatic conditions in the first half of the last millennium as reconstructed from paleoclimate data. And here coral records suggest that ENSO and IOD variability was reduced by about 30% at the same time as there's evidence for dry conditions, more droughts, even mega droughts in the northern and southern mid-latitudes. Then in the second half of the last millennium, ENSO and IOD variability increased again at the same time as there being evidence for wetter conditions, fewer droughts across the mid-latitudes. And so this begs the question of why? And also, would this relationship hold in either direction if we see future changes in the magnitude of ENSO and IOD variability? Now, there are some obstacles to answering these questions. There are vanishingly few suitable paleoclimate records available to test this further, unfortunately. But even if we could prove that this relationship is robust, these very sparse point data can't tell us why. But this, of course, is where climate models can help. That is, we can test this hypothesized link between ENSO and IOD variability and droughts in the mid-latitudes by running targeted climate model experiments. And so for this, we've used the ACCESS-ESM 1.5, a fully coupled system model that you've probably all heard about a lot. You can read all the details about it on the Hive. And what we've done with the ACCESS-ESM is to alter or prescribe the magnitude of sea surface temperature variability in the tropical Indian and Pacific Oceans to see how that affects rainfall, and then run those simulations for many centuries so that we have enough time to get some reasonable drought statistics. So here I'm showing a summary of the 4 experiments that we ran compared with the control. In the middle, the plots just show the total range of monthly sea surface temperatures. So for example, here is where we reduced the magnitude of Indo-Pacific sea surface temperature variability by 30% compared with the control. So notionally, the equivalent of the first half of the last millennium. But we also decreased the variability by 60%, like on the left, and increased it by 30 or 60%. And we ran each of these simulations for 600 years. As to how we did this practically, I mean, if you want the details, you can talk to myself or Spencer or read all about it on the Hive forum. But just in brief, I took as a sort of template the existing 1,000-year-long pre-industrial control run for this model, increased or decreased the size of the sea surface temperature anomalies with respect to the monthly climatology, made a mask to show the model where we wanted to restore the sea surface temperatures. So outside of that, and for every other variable, the model is allowed to evolve freely. And there's a bit of finagling to feed the files to the model, to tell it to nudge the sea surface temperatures to be what we want, and then set it off on its merry way. So that's how we did it. Now let's look at some results. So first we want to check that the sea surface temperature perturbations have worked as planned. This plot shows that they did. So in the top row, I'm showing sea surface temperature anomalies in the Niño 3.4 region. The bottom row is the dipole mode index for the strength of the Indian Ocean dipole. The blue lines are where we increase the magnitude of tropical Indo-Pacific sea surface temperature variability. The red lines are where we decreased it. The dashed black line is the control. So everything looks good there. So now let's start by having a look at just the changes in the long-term rainfall patterns. So here I'm showing the difference in mean annual precipitation for each experiment compared with the control. The panels will all be laid out in the same way. So on the top row, we have the experiments where we decrease the magnitude of the sea surface temperature variability by 60 or 30%. The bottom row is where we increase the magnitude of sea surface temperature variability. And in the interests of time, I'll mainly focus on Australia. So we can see here that when we decrease ENSO and IOD variability, it's drier on average in the ACCESS-ESM across Eastern Australia, but with increased average annual rainfall across sort of India, Arabian Peninsula, Horn of Africa, southwestern US. Southwestern Australia. When we increase the magnitude of ENSO and IOD variability, there's actually not a lot of change in Australian rainfall, although some larger changes around the Indian Ocean. And so if you're looking at this, you might be thinking something like, oh, well, we better not squish down ENSO and IOD variability or it won't rain in Eastern Australia. And if you lived inside the ACCESS-ESM, you might indeed be right. But of course, there is more to the story than this. So now we're looking at interannual rainfall variability as summarized by this metric, the coefficient of variation. And here we can see that when ENSO and IOD variability is decreased, year-to-year rainfall variability across the entire Australian continent is actually increased. Conversely, when ENSO and IOD variability increases, there is less year-to-year rainfall variability across the Australian continent and indeed a lot of the tropics and mid-latitudes. Okay, so to very briefly summarise, when we decrease tropical Indo-Pacific sea surface temperature variability, it's sort of a case of drought or deluge across the whole Australian continent, although Eastern Australia is drier on average. But then if we increase the magnitude of ENSO and IOD variability, there is less year-to-year rainfall variability across quite a lot of the globe. Okay, so that's great. We've had a look at how changing the magnitude of tropical Indo-Pacific sea surface temperature variability affects long-term rainfall statistics in the ACCESS-ESM. Now we'll have a look at droughts, where unfortunately, as is often the case when we reduce the degrees of freedom, things are somewhat less straightforward. So here I'm showing in the top panel the length of all multi-year droughts, that occur in a 600-year simulation. In the bottom panel is the severity of those droughts, so how much rain is missing compared to the climatological average. These are for the locations exactly matching the locations of the specific paleoclimate records that were used to identify hydroclimatic conditions in our hypothesis. And then in each case, there are 2 violin and box plots. In the grey is the range of values from the pre-industrial control, and then in the cream are the values from the simulation where we reduced ENSO and IOD variability by 30%, so as per our hypothesis. But in this model, at least, it looks like our hypothesis is not strongly supported. So that is, when we decrease the magnitude of ENSO and IOD variability in the ACCESS-ESM, we don't see a significant shift to longer or more severe droughts in these locations. There's maybe a hint of a tendency in that direction, but more so for East Africa and southwestern US than for Australia in the middle. Now, there's a lot more we could get into here, but in the interest of time, I'll skip over that. Also, if you've been patiently waiting to hear about the mechanisms for this, then you are going to be leaving disappointed. These simulations are pretty fresh off the supercomputer, so I haven't had time to get into it. If you're coming to AGU, then hopefully I'll have some more by then. Also, I just wanted to finish up by saying that after some sort of teething issues that were all very nicely dealt with by Spencer, it was pretty easy to do the sea surface temperature perturbations, even for a total beginner. So before embarking on this project, I'd never run a climate model before. This is my post on the Hive forum earlier this year begging for guidance. So I would encourage any of you with an idea and a plan to test it to jump in and have a go. All right, so here's a summary of my main points and my future plans, which you can read at your leisure, and I will invite questions, although I won't promise that I can answer them.
Questions?
So you've made your temperatures with increased or decreased variance, presumably just by multiplying the PI control by a number?
But then everything in the PI control would be multiplied by that number, right? Whereas we wanted to see what happened.
Okay, sure.
Yeah.
Everything in that region is what you prescribed. Like the
yes. So we only prescribed the sea surface temperature anomalies in the Indo-Pacific.
Yeah.
Outside of that.
But those sea surface temperature anomalies that you prescribed in the Indo-Pacific were linearly scaled from the PI control.
Yes, they were.
So we know that ENSO changes in amplitude and variance tend to be linked to different spatial patterns and different frequencies. Would you expect those to be?
I was going to say, please see my future plans. Yes, so I think just due to we'll probably have to test these things with differently set up simulations. So actually Spencer and I are meeting at lunchtime to discuss practically how we would do things like have a look at the effects of event sequencing or a different mean state, so more El Nino-like, La Nina-like. I think figuring out how to do that practically in the model is our current question. Because I would expect the results to be different.
Cool.
Yeah. Thanks.
More questions? Yes, go Khan.
So if I understand correctly what you did, you're essentially restoring, I don't know what the time scale is.
3 days.
3 days, rather strongly. So that would probably create artificial circulation patterns in the upper ocean. Another thing that worries me is that by restoring to the existing PI control SSTs, you are eliminating the feedback of the evolving mid-latitudes or higher latitudes onto the Pacific SST. And I'm not sure how to isolate the impacts of that thing from your results.
Yes, so I've thought about this and would be extremely pleased to hear your or anyone else's thoughts on how we could deal with that, how we could do something like this, see, test these increased or decreased magnitude of variability without these sort of artificial, these effects. Because I really thought about this before embarking on this project, but was not clever enough or didn't understand models well enough to figure out how to do it. So I'd be super keen if anyone has thoughts on that. Sorry, that's an unsatisfying answer, but it's the sad truth.
We'll take one more question. Can I ask the lightning speakers to please stand up and get organised at the front?
Is this using the regular PI control, or did you run a version with just fixed original magnitude?
No, so we use the regular PI control, just sort of thinking along these lines that we did want there to be some sort of the longer scale variability, lower frequencies.
Yes, it'd be interesting to do it with the fix just to see if that has an impact on anything, because
That's a good
potentially
idea. Yep.
you are mucking up the relationship between the tropics and the higher latitudes by fixing.
Yeah, closer to a regular pacemaker type.
Yeah, just
Yeah.
with the one times the amplitude, but
Yeah, thanks. Yep.
I don't know.
Okay, thank you, Georgina.